Welcome! In this session, we'll explore an exciting problem from LeetCode, problem number 973, k closest points to origin. This problem challenges us to find the k closest points to the origin, 0, 0, from a given set of points. We'll dive into efficient strategies to solve this and understand key concepts along the way. Let's get started. The problem is called k closest points to origin. You are given an array of points, where each point is represented as a pair of integers, x underscore I, y underscore I, on a two-dimensional plane. Along with this, you are provided an integer k, and your task is to return the k points from the array that are closest to the origin, 0, 0. The distance between 2 points on the plane is calculated using the Euclidean distance formula, which is the square root of the sum of the squares of the differences in their x and y coordinates. Since we are measuring the distance specifically from the origin, the formula simplifies to the square root of x underscore I caret 2 plus y underscore I caret 2. As part of the requirements, the order in which you return the points does not matter, and you can assume the result will always be unique, meaning there will be no ties that need breaking. To summarize the input format, you are given a list of n points, where each point is represented as a pair of two integers, x underscore I, y underscore I. For example, the points could be 3, 3, 5, -1, -2, 4. Alongside this, you are provided an integer k, like k equals 2, which specifies the number of closest points you need to return. The output format is a list of k points selected from the input array, each point represented as a pair of integers. These points should be the ones closest to the origin based on their Euclidean distance. However, the order in which the points appear in the output does not matter. For instance, with k equals 2, the output could be 3, 3, -2, 4, or -2, 4, 3, 3. Let's now look at some examples to illustrate this further. In the first example, the input points are 1, 3, -2, 2, and k is 1. This means we are looking for the single point that is closest to the origin. To calculate the distances, we use the Euclidean distance formula. For the point 1, 3, the distance is the square root of 1 caret 2 plus 3 caret 2, which equals sqrt, 10. For the point -2, 2, the distance is the square root of -2 caret 2 plus 2 caret 2, which equals sqrt, 8. Since sqrt, 8, is smaller than sqrt, 10, the closest point is -2, 2. Therefore, the output for this example is -2, 2. In the second example, the input points are 3, 3, 5, -1, -2, 4, and k is 2. This means we need to find the two closest points to the origin. Calculating the distances, the point 3, 3 has a distance of sqrt, 3 squared plus 3 squared, which equals sqrt, 18. The point 5, -1 has a distance of sqrt 5 squared plus -1 caret 2, which equals sqrt 26. Finally, the point -2, 4 has a distance of sqrt -2 caret 2 plus 4 squared, which equals sqrt 20. Among these, the two smallest distances are sqrt 18 and sqrt 20, corresponding to the points 3, 3, and -2, 4. Thus, the output is 3, 3, -2, 4, and the order of the points can vary. In the third example, the input points are 0, 1, 1, 0, and k is 2. This means we need to return both points, as the total number of points equals k. Calculating the distances, the point 0, 1 has a distance of sqrt 0 squared plus 1 squared, which equals sqrt 1. Similarly, the point 1, 0 also has a distance of sqrt 1 squared plus 0 squared, which equals sqrt 1. Since both points are at the same distance from the origin, and we are required to return k equals 2 points, the output is 0, 1, 1, 0. Both points are included in the result. There are a few constraints and edge cases to keep in mind for this problem. First, the value of k will always be between 1 and n, where n is the total number of points, and n can go up to 10, 0, 0, 0. The coordinates of each point, x underscore I and y underscore I, are integers that lie within the range of -10, 0, 0, 0 to 10, 0, 0, 0. The uniqueness of the result is guaranteed, so there is no ambiguity in the solution. For edge cases, if there is only one point in the input and k is 1, then the output is simply that single point. If all the points have the same distance to the origin, any k points from the input can be returned. For large inputs where n and k approach their upper limits, the solution should be optimized for efficiency. Finally, points with negative coordinates are handled naturally by the formula, as squaring the values ensures distances are always positive. To solve the problem of finding the k closest points to the origin, we first considered the brute force approach. The intuition here is simple: calculate the Euclidean distance for each point, sort all the points based on that distance, and then return the first k points from the sorted list. Specifically, we calculate the distance as x2 plus y2. Notice that there's no need to take the square root since we are only comparing relative distances. After calculating the distance for each point, we pair each point with its distance, sort the entire array, and pick the top k. However, this approach has some downsides. While it's straightforward, sorting the entire list of points takes n log n time, which becomes inefficient for large datasets. Additionally, it requires n extra space to store the distances, making it less optimal when only the k smallest elements are needed. This is why we explored alternatives to improve both performance and memory usage. Next, we looked at an optimized approach using a min heap. Here, the idea is to load all the points into a min heap, where the key used to organize the heap is the distance of each point from the origin. Once all points are in the heap, we extract the k smallest points directly. While this improves on the brute force method, as it avoids sorting the entire array, the time complexity is still n log n, because inserting each of the n points into the heap takes log n, and we perform this operation n times. Additionally, extracting the k points adds k log n. The space complexity remains n, since the heap must store all points initially. While this approach is better than brute force when k is small, it still processes all points, which is unnecessary when we only care about the k closest points. This led us to our chosen approach, the max heap strategy, which is even more efficient. We ultimately selected the max heap approach due to its efficiency and scalability. The key insight is that we don't need to sort all points or even keep track of every point's distance. Instead, we maintain a max heap of size k to store only the k closest points. As we iterate through the points, we calculate the distance for each one and push it into the heap. If the heap size exceeds k, we remove the point with the largest distance, ensuring the heap always contains the k closest points. This reduces the time complexity to n log k, as each heap operation, both insertion and removal, takes log k, and we perform these operations for all n points. The space complexity also improves to k, since the heap size is limited to k. Compared to the brute force and min heap approaches, this method avoids unnecessary computations and minimizes memory usage, making it ideal for cases where k is much smaller than n. The key realization here was that we don't need to process or store all points, just the k closest. This insight significantly reduces both computational overhead and space requirements, making the max heap approach the optimal solution for this problem. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. This code solves the LeetCode problem k closest points to origin using a max heap priority queue. The goal is to return the k closest points to the origin from a list of 2D points, based on their squared Euclidean distance. The k closest method starts by initializing an empty list max_heap, which will store the closest points dynamically. Python's heap module is used to manage this heap. Since Python's heap provides a min heap by default, we insert the negative of the squared distance to simulate a max heap. The method iterates over each point, x, y, in the input list points. For each point, the squared distance from the origin is computed as x*x plus y*y. This avoids the computational overhead of calculating the square root, which is unnecessary for comparison purposes. We push a tuple, distance, x, y, into the heap. The negative distance ensures that the farthest point, with the largest squared distance, is always at the top of the heap. If the heap size exceeds k, we remove the farthest point using heap.heappop to maintain only the k closest points. Finally, the method extracts the points from the heap by iterating over its elements and returning a list of x, y coordinates. The result is the k closest points to the origin. This approach is efficient, with a time complexity of n*log k, where n is the number of points and k is the required number of closest points. The space complexity is O, k, due to the heap size being limited to k elements. This solution handles edge cases such as k being 0 or the input list being empty, as the heap operations naturally account for these scenarios. Here, we're using a priority queue to solve the problem of finding the k closest points to the origin. The idea is to leverage a max heap, which we implement using a custom comparator. This comparator sorts the points based on their squared Euclidean distance from the origin, but in descending order. This ensures that the point farthest from the origin is always at the top of the heap. Next, we iterate through each point in the input array. For every point, we add it to the max heap using the offer method. If the size of the heap exceeds k, we remove the farthest point by calling poll, which ensures the heap only contains the k closest points at any time. This way, we maintain efficiency as we process the points, ensuring that no unnecessary elements remain in the heap. Finally, we construct the result array to store the k closest points. Using a simple while loop, we extract points from the heap one by one using the poll method and store them in the result array. The index variable helps us insert points sequentially into the array. Once all points have been extracted, we return the result. This implementation is efficient because the heap maintains a size of k, and operations like insertion and removal are logarithmic in complexity. Thus, the overall approach ensures we're optimizing both time and space while solving the problem effectively. We begin with the input points 1, 3, 2, 2, 2, minus 2, and k equals 2, meaning we want the 2 points closest to the origin. First, we initialize an empty max heap, which we'll use to keep track of the k closest points. Next, we process the point 1, 3. The squared distance from the origin is calculated as 1/2 plus 3 squared equals 10. To store this in our heap, we push the negative of the distance along with the point coordinates as -10, 1, 3, so the heap now contains -10, 1, 3. Moving on, we process the second point, -2, 2. The squared distance is -2, 2 plus 2 squared equals 8. We push this into the heap as -8, -2, 2, resulting in a heap state of -10, 1, 3, -8, -2, 2. Next, we process the point 2, -2. The squared distance is calculated as 2 2 plus -2, 2 equals 8. We push this into the heap as -8, 2, -2, updating the heap state to -10, 1, 3, -8, -2, 2, -8, 2, -2. At this point, the heap has more than k elements, so we remove the farthest point, which is the one with the smallest negative distance, -10, 1, 3. After removing it, the heap state becomes -8, -2, 2, -8, 2, -2. Finally, we extract the points stored in the heap, which are -2, 2, 2, -2. These represent the 2 points closest to the origin, so our output is 2, -2, -2, 2. For the next example, we have the input points 3, 3, 5, -1, -2, 4, and k equals 1. This time, we want just the single closest point to the origin. First, we initialize an empty max heap. We then process the point 3, 3, calculating its squared distance as 3 2 plus 3 squared equals 18. We push this into the heap as -18, 3, 3, so the heap now contains -18, 3, 3. Next, we move to the point 5, -1. The squared distance is 5 2 plus -1, 2 equals 26. We push this into the heap as -26, 5, -1, resulting in a heap state of -26, 5, -1, -18, 3, 3. Since the heap now has more than k elements, the farthest point, -26, 5, -1, is removed, leaving the heap as -18, 3, 3. Next, we process the point, -2, 4. The squared distance is calculated as -2, 2 plus 4 squared equals 20. We push this into the heap as -20, -2, 4, which updates the heap state to -20, -2, 4, -18, 3, 3. Again, since the heap contains more than k elements, the farthest point, -20, -2, 4, is removed, leaving the heap with -18, 3, 3. Finally, we extract the points in the heap, which gives us 3, 3. This represents the single closest point to the origin, so the output is 3, 3. In this example, the input points are 0, 1, 1, 0, 2, 2, and k equals 3, meaning we want all 3 points since k equals the number of input points. First, we initialize an empty max heap. We then process the point 0, 1, calculating its squared distance as 0, 2 plus 1 squared equals 1. We push this into the heap as -1, 0, 1, so the heap state becomes -1, 0, 1. Next, we process the point 1, 0. The squared distance is 1, 2 plus 0 squared equals 1. We push this into the heap as -1, 1, 0, which results in a heap state of -1, 0, 1, -1, 1, 0. Finally, we process the point 2, 2. The squared distance is calculated as 2, 2 plus 2 squared equals 8. We push this into the heap as -8, 2, 2, updating the heap state to -8, 2, 2, -1, 1, 0, -1, 0, 1. Since k equals the total number of points, we do not remove any elements from the heap. We then extract the points from the heap, which are 2, 2, 1, 0, 0, 1. These represent all the points closest to the origin within the given input, so the output is 2, 2, 1, 0, 0, 1. To understand the time complexity of our solution, let's start by analyzing the main components of the code. First, we iterate over all the points in the input list. Each point is represented as a pair of coordinates, x, y. For every point, we calculate its squared distance from the origin using the formula distance equals x asterisk x plus y asterisk y, which is a constant time operation, O(1). Since we process all n points, the total time for this step is O(n). Next, we use heap operations to maintain the k closest points. For each point, we insert it into a max heap using the heap.heap push operation, which takes O log k time. If the heap exceeds k elements, we remove the farthest point using heap.heap_pop, which also takes O log k. Therefore, for all n points, the total time spent on heap operations is O(n asterisk log k). After processing all the points, the final step is to extract the k closest points from the heap. The heap contains at most k elements, so iterating through it to construct the result takes k time. When we sum up all the components, we have O(n) for iterating over the points, O(n asterisk log k) for heap operations, and O(k) for extracting the results. The dominant term here is O(n asterisk log k), which gives us the overall time complexity of the solution. Now, turning to the space complexity, the main contributor is the max heap. The heap stores at most k elements at any moment, requiring k space. Additionally, the input list of n points takes n space, but since it's part of the input, it's not counted as auxiliary space. The output, which is a list of the k closest points, also requires k space. Apart from these, we use a few extra variables such as distance, x, y, and the loop iterator, all of which require constant space, O(1). When we sum up the space usage, we have OK for the heap, O(n) for the input, OK for the output, and O(1) for the variables. Among these, the dominant term for auxiliary space is OK, so the overall auxiliary space complexity is OK. This reflects the efficiency of the heap-based approach, as the space usage is proportional to the number of closest points we need to maintain, rather than the total number of points in the input. To better understand the efficiency of our approach, let's compare it to the brute force method. In the naive solution, we would compute the squared distances for all n points, which takes n time, and then sort the points based on their distances, which takes n asterisk log n. Finally, extracting the first k points takes k, making the total time complexity n asterisk log n. The space complexity of the brute force approach is n, as it requires space for the sorted list. In contrast, the heap-based solution avoids sorting the entire list. By maintaining only the k closest points in the heap, it reduces the sorting overhead. This results in a time complexity of n asterisk log k, which is significantly faster when k is much smaller than n. The space complexity is also reduced to k, since the heap only stores k elements. This makes the heap-based solution optimal for scenarios where k is much smaller than n, providing both time and space efficiency over the brute force method. One common mistake when solving this problem is calculating the full Euclidean distance by including the square root operation. While this might seem intuitive, it's not necessary. The relative order of distances remains the same if we use the squared distance, which is simply x squared plus y squared. This avoids the computational cost of the square root and makes the solution more efficient. Another mistake is sorting the entire list of points to find the closest k. Sorting takes n log n time, which is wasteful when we only need the top k points. A better approach is to use a heap, which can efficiently manage the k closest points as we process the input. Lastly, some people overlook how to handle ties when multiple points have the same distance to the origin. Neglecting this can result in inconsistent outputs, particularly if the problem doesn't specify an order for such cases. Always account for these scenarios to ensure correctness. Another pitfall is misunderstanding how priority queues, or heaps, function in this context. For example, using a max heap when a min heap is required, or vice versa, can lead to incorrect behavior. In a k-size max heap, the farthest point is kept at the root, which allows you to efficiently remove it when a closer point is found. This is the correct approach for maintaining the k closest points. Additionally, edge cases require special attention. For instance, what happens if k is greater than the total number of points? Or if k equals 0? These scenarios can lead to runtime errors or incorrect results if not properly handled. Always validate edge cases to ensure your solution is robust and handles all possible inputs gracefully. From an interview perspective, optimization is often a key focus. Interviewers want to see that you can go beyond brute force solutions. For this problem, using a priority queue or the quick select algorithm demonstrates a deeper understanding of efficiency. It's also important to clarify edge cases at the outset, such as whether points can overlap or if k might exceed the number of points. This shows that you're thinking critically about the problem. Furthermore, be prepared to explain your choices. For example, why did you choose a heap over quick select, or what trade-offs are involved in terms of time and space complexity? Another strong approach is to iteratively refine your solution. Start with a basic implementation and improve it step by step, as this demonstrates structured problem solving. Finally, be aware of variations where the distance metric might change. For example, instead of Euclidean distance, the problem could use Manhattan distance. Flexibility in adapting your solution to such changes is an asset. Related problems like finding the kth largest element or the top k frequent elements are great practice for sharpening your heap-based skills. When considering alternative approaches, each comes with its own trade-offs. The heap-based approach is a popular choice, with a time complexity of n log k. This is efficient for handling large datasets when k is small, but it does require extra space to maintain the heap. Another option is the quick select algorithm, which has an average case complexity of n, but can degrade to n squared in the worst case. It's faster in expectation but may be harder to implement correctly under interview pressure. Brute force, which involves sorting the entire list, is straightforward to implement but inefficient for large inputs due to its n log n complexity. Finally, there's the divide and conquer method, which is rarely used but can be adapted for specific distance metrics. While it's flexible, it's often overkill for standard Euclidean distance problems. Understanding these trade-offs ensures you can select the best approach for the given constraints and explain your reasoning effectively. Great job! We've covered the k closest points to origin problem. You learned how to use a max heap to efficiently find the k closest points, along with its time and space complexities. This is a valuable technique for proximity-based problems. Thanks for watching. Be sure to like, share, and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!